8225, represent geometric sequences using equations, tables, graphs, and verbal descriptions, and use them to solve problems. Remember, the equation for the geometric sequence is f of x equals ab to the power of x. X is your exponent. Actually, in a geometric sequence, when you have that x for an exponent, this is actually called an exponential graph, hence exponent being x. So remember, a represents your starting point, or the number that you need to start with. The b value is your common difference, and again, you find that through multiplication, so you figure out what it's being multiplied by to get that y value. And x would represent basically your duration. Normally it's years, doesn't always have to be, but it's some time frame. So here in example 1, it says in 2010 the population of Edina, Minnesota was about 45,600. Suppose that the population is predicted to double every 10 years. So it's going to double every 10 years. Here's your starting point. So if you use that equation in part A, it says write an equation that can be used to predict the population after x 10-year periods. X 10-year periods. Here's our original formula, so let's go ahead and put in the information that we know. We know that the a value there is your starting point. So what is that starting population? Well, that was the 2010 population of 45,600, so that is our a value. Your b value is your common difference. It's found by multiplication. Well, multiplication is happening right here. You're doubling it. So in for b, we'll go 2. And then x represents how many 10-year periods. So that would be the equation to figure out how many 10-year periods in the population. This would be your predictor equation. Part B, it says that you actually have to use your predictor equation to figure out what the population would be in Edina in 2040. Well, remember, 2010 is when we started. So 2040 and 2010, our difference is 30 years. And we need to, our equation here, x represents how many 10-year periods that we had. This is 3 10-year periods. So we need to put in 3 for x. So I'm going to substitute 3 in for x. Do your order of operations. Says that you need to take care of the exponent first, so we take care of that. We'd have our starting value. I would figure out what is 2 to the third power. 2 to the third power would give me 8. So then I would multiply 45,600 times 8, and I wind up with 364,800 people. Example 2, in the function f of x equals 3 to the power of x, if a positive value of x is increased by 2. So let's say x is going to increase by 2. We want to know what is the effect on the value of the function. So set up a table like you've done before. Here's x, there's y. It says that if a positive value of x, so you need to come up with a positive value of x. Well, 0 is neutral, so that wouldn't be positive. So I'm going to go ahead and start with 2. 2 is positive. Well, when we increase it by 2, when you increase your x value by 2, so that would be 4, 6, so on. We want to know what is the effect that it has on this function. So what we would do is put in your x value into this equation up here. So if I substitute in 2 for x, that is 3 to the second power, which would give me 9. Substitute in 4 for x, and we would get 81. Substitute in 6 for x, and we get 729. Now we need to figure out the pattern. Well, this is increasing by 2, as it should. And this here, well, to get from 9 to 81, I multiply by 9. I check it out again, multiply by 9. So as the x value increases by 2, your y value is going to multiply by 9, which would be option C. Example 6, the half-life of a certain substance is how long it takes for there to be only half of the substance remaining. For 200 grams of the substance, the geometric sequence given by the function f of x equals 200, 1/2 to the power of x tells us how much of the substance remains after x lives. Which graph represents this situation? One thing to know about these, when you have a power of x, your graph will look like this. It's just a curve, and all of a sudden it will go fast. Otherwise, it'll start up here and curve down drastically. But that's what your exponential graphs will look like. We know example C, that's a straight line. That's a linear graph. That's y equals mx plus b. This is a quadratic function. In order for that to happen, notice how x has an exponent of 1 here. This happens when x is squared, and that can be positive or negative as well. But our two options for A and B, these would be our only exponential graphs. And if you actually go ahead and use a plug and play here, so I'll just plug those values in for x in for that graph. I put in 0. When I put in 0 into that equation there, I get 200. When I put in 1, I get 100. When I put in 2, I get 50. So basically what this graph is telling you, as x increases, y is decreasing. So I look at my graph, and if you look at graph A, this is your answer. Okay? Why? Because when x is increasing, notice what's happening to y. Y is decreasing. So option A would be our only answer. This will conclude 8225.